Today, we're diving into a real-life engineering mystery. It was a system that worked for years until one day it didn't. The pipeline was installed back in 2008. It was made of glass fiber reinforced epoxy, and it connected to a steel riser. There was a 3-meter section left completely unsupported. No bedding, no bracing, just hanging there in the soil. And that detail, it turns out to be a critical clue. Because over time, even small ground movements, natural settling, temperature shifts, seasonal freeze-thaw can put significant stress on unsupported pipe sections, especially at junction points like risers. Fast forward to 2023. Inspectors began noticing something strange: circumferential cracks. Cracks that ran around the pipe like a tight band, almost like someone had wrapped the pipeline in a squeezing force and crushed it from the outside. Picture a drinking straw. You squeeze it from the sides, it buckles. That's what these cracks looked like. But here's the thing. Those cracks weren't the problem. They were the symptom, a visible sign that something deeper was going wrong. The real issue? That misaligned riser. Over the years, as the ground shifted and the riser settled unevenly, it put increasing pressure on that unsupported section of pipeline, bending it, stressing it, slowly weakening it, until eventually the cracks began to appear. And just when you think you've solved the mystery, enter water hammer, a pressure surge caused by the sudden stop of flowing fluid. Now scale that up to pipeline size. In 2023, the operators increased the volume of fluid running through this pipeline. More flow, more momentum, and with it, more violent pressure surges. Shock waves hitting the pipe over and over again, right at its weakest point, that cracked section near the riser. It's a 1-2 punch. Long-term bending and stress create cracks. Then repeated water hammer blows hammer those cracks open. The engineering report that followed this failure reads like forensic evidence. Visual inspections, pressure data, crack mapping, even graphs showing the before and after pressure jumps following the increased flow rate. And here's the kicker. They calculated the water hammer force. These weren't guesses. The numbers told the full story. The damage wasn't random. It was mechanical, predictable, preventable. But the report wasn't just about solving the failure. It was about how to prevent the next one. Let's break down the recommendations. First, support the riser. That unsupported 3-meter stretch, it never should have been left hanging, especially in a zone where soil movement is expected. Better bedding, more structural support, it's basic but critical. Think of the riser as the weakest link in the chain. Support it, and you strengthen the whole system. Second, control flow increases gradually. That sudden bump in volume, it triggered stronger water hammer events. Even if fast flow-ups are needed for operations, they can be made safer by ramping up in controlled increments. Third, use surge protection devices. They act like shock absorbers for pipelines. When pressure spikes hit, these devices absorb the energy, reducing the impact on the pipe walls. Simple tech, huge difference. And maybe the most important lesson? Always factor in real-world forces. Not just design specs, but soil conditions, operational changes, material behaviors. That's how you avoid surprises. Because here's the truth. Even the strongest looking system can break if it's not maintained, supported, and reevaluated as conditions evolve. This case was never just about one pipeline. It's about how we think, how we plan, and how we learn. Failures like this aren't just accidents. They're feedback. They show us where systems are vulnerable, and they give us a roadmap for doing better. So if there's one takeaway from this story, it's that understanding the forces, mechanical, environmental, and operational, is essential. Thanks for joining us on this deep dive.